So to begin to talk about the process of factoring, the factoring process really is multiplication in reverse, in a way. What we'd like to do is begin by thinking about what it means to factor a couple of numbers. So real quick, before we start thinking about the algebraic expressions side of the house, let's ask the question, what does it mean to factor a couple of numbers? So what does it mean to quote-unquote factor? And let's pick a number here. Let's say I pick the number 280. If I were just to ask you, what does it mean to factor that number? What would you tell me? When we think of factoring, we often think about trees. So what is a tree going to do for us in this problem if I want to factor the number 280? What does it look like? Okay, so you start out with your number, 280, and you're asking the question, you identified the number 10. Why is 10 an important number in this problem? Right, so 10 is a number which goes evenly into 280, and therefore, we can write 280 as 10 times something. What is it, 10 times what? 28, right. So what we can say, just by virtue of terminology, is that 10 is a factor of the number 280. And keep in mind here, we're using the word factor because the way that these numbers piece back together to give us 280 is that they multiply, right? That language, whenever you hear the word factor, you should think in your mind multiplication and division. Those are the operations we're most concerned with right now. So 10 is a factor of 280 because 10 times 28 is equal to 280. By the same token, we can say 28 is a factor of 280 because 10 times 28 is equal to 280. And so what that does is it begins the process of breaking apart the number 280 into its constituent pieces. And usually the way that we would draw that, if we like factor trees, is we would draw a couple of little lines underneath it here. And then at the ends of those lines, we would put these two factors, 10 and 28. So we interpret this to mean that 28 times 10 gives us 280, the number that's at the top of their little branch of the tree. So far, so good? This is one of many different ways that we could start this factor tree. The answers that we get at the end of the tree should all be the same, but we may take different routes to get there. So if you decide to start in a different way than 10 times 28, that could be just as fine. So then what happens next? We've broken apart 280 into 10 times 28. Maddie? Factor each of those numbers. Let's look at 10 for starters. How can we factor the number 10? 5 and 2. So I can break 10 into 5 times 2. And again, writing that as a tree because 5 times 2 gives us 10, which is at the top of its branch. How about 28? 4 and 7. So 4 and 7, because 7 times 4 gives us 28. So now, at this stage in the game, we've broken apart 280 into a product of 4 different things. Not just 10 times 28, but breaking it down further, we could write 280 as 5 times 2 times 4 times 7. Right? What will we then do? What comes next? Maddie? Right, see if we can break down any of these numbers any further. 5? 2? 4? Okay, so how do we break 4 apart? 2 and 2. That's the only way of doing it that's not what we call trivial, right? We could break any of these numbers, if we wanted to, apart into itself times 1, right? 5 is 5 times 1. But that's not very interesting, because that doesn't give us a breakdown that tells us anything new about the number. But 4 we can break apart into 2 times 2. 7? 7 we can't break apart any further. So what do we call the numbers that are at the ends of these branches? The numbers for which we are done breaking them down. Yeah. So those are the most basic factors that exist for a whole number. They can't be broken apart any further because their only factors are themselves and 1. We call those numbers primes. So these numbers here at the ends of the branches are primes. That's how we know that we're done factoring. And so the beauty of this method is even if we take different routes to get to the bottom of the branches of this tree, you and I will always end up with the same numbers, even if they're in different order. We're going to end up with the same primes at the ends of our branches. And what it allows us to do is to say 280 is equal to, and I'm going to rearrange these primes just so that they're in increasing order for no particular reason, 2 times 2 times 2 times 5 times 7. I've got to make one of these 2's blue just to coordinate with our table. And what we get out of this is a quantity called the prime factorization of 280. And if we understand the prime factorization of a number, or of any quantity in general, then we understand completely how it's pieced together from smaller pieces, from smaller factors. It's also conventional, just to save some space, to rewrite this prime factorization in a way that avoids us having to repeat factors. So what's a better way to write 2 times 2 times 2? 2 to the power 3, exactly. 2 to the third. And then maybe I'll put, just for emphasis, an exponent of 1 on the 5 and an exponent of 1 on the 7. So there's the prime factorization of the number 280.